We're exploring NASA's first tabletop roleplay game and a new way to potentially find worlds with water on their surfaces. This week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. If you're a space fan with a dice collection and a love of the Hubble Space Telescope, you're in for a treat. Today, we're going to dive into the Lost Universe, NASA's first tabletop roleplay game with Christina Mitchell, a senior multimedia specialist at NASA's Goddard Space Flight Center. Then we'll shift our gaze from the mythical to the methodical with Amaury Triaud, an astronomer from the University of Birmingham in the UK. He and his colleagues have found a new way to potentially detect liquid water on the surfaces of terrestrial exoplanets. Then we'll connect with our chief scientist, Dr. Bruce Betts, for What's Up and a new random space fact. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. As a side note, I got a bit of a cold while I was traveling to go see the April 8th total solar eclipse. But hopefully my croakiness won't take away from the awesome science in the show. If you're a fan of games like Dungeons & Dragons or Pathfinder, you'll be happy to hear that NASA has released their first tabletop roleplay game. I've been an avid fan of these kinds of games since I was very young. At the end of my time in college, I spent my nights scanning the sky looking for exoplanets going around other distant stars. But by day, I paid my bills by working at a tabletop gaming store. Tabletop roleplay games allow players to assume the roles of characters in the game, acting out their part as they're guided through their adventure by a game master. Tabletop roleplay games, or TTRPGs for short, blend storytelling and strategy, as players explore worlds with dice, paper, and the power of the imagination. I know, it's totally nerdy, but it's so much fun. Now our friends at Hubble, NASA, and the Goddard Space Flight Center have created their own tabletop RPG called The Lost Universe. Our first guest today is Christina Mitchell. She's a senior multimedia specialist at NASA's Goddard Space Flight Center in Greenbelt, Maryland. Christina led the creation of this new and beautiful game.
Thanks for joining me, Christina.
Thanks for having me.
So I'm a huge space nerd, but my second greatest passion is gaming. Dungeons & Dragons and Pathfinder and all these tabletop RPGs played such a huge role for me growing up, but also for a lot of my coworkers, and I'm sure for so many space fans around the world. So I was so excited to hear that NASA had finally come out with a tabletop RPG, and my first question is, what sparked the Hubble team's interest in creating this kind of roleplay adventure?
Well, it started outside the Hubble team. So I work more generally in the Office of Communications. So I'm a big fan of tabletop games myself. I play very often. I watch actual plays and things like that. So it just sort of occurred to me one day that there's a lot of crossover between space fans and tabletop fans. And that's an audience that we really have never reached out to specifically. So from there, it sort of snowballed in my mind until it became, we should do this. So I called up my boss one day and I was like, hey, I have this absolutely insane idea. And at first, nobody really understood what it was or what I was trying to do, but I pitched it to the Hubble team to see if they wanted to support it. And luckily, they bought in. So from there, we were able to develop it.
There is so much that goes into creating a tabletop RPG. And the way I'm kind of thinking about this is it's more of a module or a single adventure rather than an entire roleplay system. So what existing systems is it compatible with?
It can be adapted to pretty much anything. We did write it with like a D20 base in mind, since those tend to be the most common, but it wouldn't be difficult at all to adapt to any other systems. We tried to keep it all very generic, very system agnostic, so it'd be as accessible as possible.
And for some of the people out there who might not be familiar, a D20 is a 20-sided die, which is like the core die that you use in so many of these systems. And what I personally use to figure out who our space trivia winners are each week. I'm glad that this exists because in many cases, my astronomy friends over the years have wanted to play a science-based, space-based RPG, and we've had to kind of put together our own systems to do this. So this is a fun opportunity to actually have one that's already put together. And the world that it presents is so interesting and beautiful. And while part of the story does take place on Earth, a huge part of it takes place on this rogue planet called Exlaris. Can you tell us a little bit about what this planet has gone through and how the story weaves together?
Yeah, so honestly, creating the setting was, I think, one of the most fun parts of the game design. Because when I started the writing of it, I was very adventure focused and didn't really have the setting nailed down. And it took a while to figure out exactly what kind of a setting really belonged. But once somebody, I think someone made the comment to me of like, hey, you should do something on like another planet. And I was like, okay, what if it's a rogue planet? And sort of spiraled from there. But yeah, so this planet, I see it as sort of a mirror of Earth in a way, where it was within a solar system, it was in its star's habitable zone. There was a civilization that was flourishing. And then, like, a black hole came close enough to knock it out of its orbit and send it off on its own as a rogue planet. And the people on this world were able to tap into the energy of the vacuum, the energy of space around them, and create magic and use that to make a force field essentially around this planet to keep their atmosphere in, keep it habitable. And from there, we're able to kind of start to rebuild their society. So yeah, I had a ton of fun sort of like imagining the history of this world. Obviously, when something like that happens, there had to be ramifications for the civilization itself. It's not just going to be one day we're happily orbiting our star and the next we're a rogue planet, but hey, everything's fine. So the way I wrote it was there was this period on the planet of real chaos, real upheaval following this event. And I think that helped really create some interesting settings where you have these creatures that had been in the darkest parts of the planet now coming out. And people were hoarding whatever they could to try to survive. And cities were being ransacked and left to ruin, which is another big setting for the game, is some of the ruins. So yeah, that was just a ton of fun to put it all together like that.
And I really value that you tried to come up with a scientific basis for this magical system. Because as a science nerd, one of my biggest pet peeves is just, and magic did it. So trying to interject that it was this idea of the vacuum energy that allowed them to do that is a really cool learning opportunity. And as I was going through this book, I realized there's so much science that you've woven in. Other than vacuum energy and what's going on with that, what are some of the other scientific concepts that you're trying to explain?
The vacuum energy was, I think, really natural because it's something that we don't know a ton about. So to me, it presented a really interesting opportunity to be like, we don't know much about this thing, but what if this thing could power magic? And so that like bridged the fantasy elements back in. And we have a puzzle that goes over redshift and blue shift. We have gravitational lensing puzzles as well. And, at the beginning of the adventure, it's set on an alternate Earth. So you get to see a lens of some of the contributions that Hubble has made and what it might be like if we didn't have those.
And that's an interesting point, too. How does the story about this rogue planet careening through the void somehow connect to Earth?
Yeah, so without trying not to spoil too much of it, some things happened with the magic on this world, and Hubble got erased from Earth's timeline. So Hubble got stolen, basically, and taken to this world. And the researchers who had been looking through Hubble's data to help them learn more about their own world also went missing. So the adventurers are really on this quest, these adventurers who are people from Earth who somehow, through magic, found themselves on this other planet. it's really an adventure to rescue Hubble and these researchers and put everything back right in the timeline.
And it's such a great point because we, at this point in time, kind of take for granted the fact that we've got all these beautiful images from Hubble. It's been out there for so many decades, teaching us more about the universe. And now we have new telescopes in space, like the James Webb Space Telescope, that are kind of like the successors to what Hubble has done. But if I really take a step back and think about what it would mean for humanity if we didn't have Hubble, how that would have changed our timeline, it could have dramatic impacts on the way that we see ourselves and the universe.
Oh, absolutely. Yeah. I mean, we wouldn't know how old the universe is. We wouldn't know black holes are in the center of galaxies. I mean, we think of all the beautiful imagery that we wouldn't have. We wouldn't have the International Space Station because astronauts learned a lot from Hubble servicing missions. So there's just so many things. And then if you think about the impacts the International Space Station has had on the research on Earth, like it's just it was really interesting to see that particular element of the story come together where we were all sitting in a room thinking, okay, what else?
It also points out just how important this kind of information could be to creatures beyond Earth. If they didn't know what was going on in space, just having some of that knowledge or access to people who knew anything about it could be really powerful for them and their ability to understand their place in the universe.
Yeah, I mean, a rogue planet, like they don't really have a need for orbiting telescopes, but having this rogue planet and then having the magic system in place there, it was an interesting opportunity because, like I said, I imagine Ixalaris as sort of a mirror of Earth, and that's the way the researchers in the story also approached their connection to Earth, is they were using Hubble to try to see, on one hand, this is what our world could have been like, and on the other hand, how can we use this to help us learn more about our own position in the universe?
What do you think was your favorite part of the creation of this game?
Oh my. I loved every minute of it. I mean, from the very beginning, this has just been absolutely a passion project for me. From the moment the thought popped into my head to seeing it go out into the world and seeing all the comments and the videos and all these things come in about it, I've just loved every minute of it. Writing the adventure itself, I think, was really my baby, creating this setting. So I'm really, really proud of the setting. And part of the goal was to create a robust enough setting that if we wanted to continue doing something, or if somebody else wanted to set up a campaign outside of this one shot, there would be enough material there to be able to fill in the gaps and have this world there for people to explore. So, I really loved doing that. The playtesting, I think, might have been my favorite, though, because I was able to get friends of mine outside the agency to playtest with me. And there's an NPC there that I play in our home games that they did not know was involved at all. So that was honestly a really hilarious moment when they realized who exactly they were dealing with at one point. So that was so much fun, just putting in these little tiny Easter eggs that I know not everyone is going to get, but like the handful of people who do, it's going to be a lot of fun.
Do you have a lot of coworkers at Goddard that are into this type of gaming?
Yeah. So there was definitely no shortage of volunteers to playtest. I think we had 2 internal playtests with different players. And yeah, definitely no shortage of volunteers.
Well, we've been talking about it at the Planetary Society as well. Like for an age, we've been wanting to set up a tabletop RPG game, not just for those of us who love this type of gaming, but to teach our other coworkers who we know would be passionate about it, how to play this type of game. And as soon as we heard that this thing existed, we were like, dude, we gotta do this. So if anyone out there is listening and you want to see us play this game, perhaps, I don't know, email me or something, because maybe we could share that experience. That'd be really fun.
Oh, that would be awesome. Yeah, and if you do like stream it or something, please send it my way. I'd love to watch.
Definitely. But ultimately, this game is not just a fun opportunity for bonding, but really highlights the pivotal role that the Hubble Space Telescope has played in our understanding of the universe and really kind of the last few years of humanity and our scientific endeavors. What do you really hope that players take away from this game about Hubble?
What I really hope they take away is, first of all, how vast the universe is. I mean, it is incredibly vast. We have learned so much. I think I would love to see players take away that Hubble has been, while all the images are absolutely incredible, there has been so much more than that. And in all honesty, we don't know what else there might be. So I think that would be the main takeaway that I want people, like in terms of Hubble, is just to realize the universe is vast and we don't know what else might be out there.
And, if you're ever looking up at the stars at night, just think about all those poor rogue planets out there that just lost their stars.
Right. Think of Ixlaris.
The drama. Does NASA have any plans to create any future tabletop RPGs?
So we don't have anything else in development right now, but we are definitely tracking how this is being received. We're tracking all the online response, and we're keeping our options open in the future.
Well, I might be super biased because I love this kind of game, but I think about how many people might learn more about space through this medium because it was their new intro to this world. And I've seen what space gaming and science fiction and all these things have done to inspire whole generations of scientists. And I'm sure that somewhere out there, someone is about to learn about the vastness of the universe just because they played this game. So fingers crossed you hear from enough people that this played a role in their understanding of the universe, because I think there's something interesting here that you've tapped into.
Yeah, I mean, it's absolutely incredible. And like you said, it's the education element too, right? Where kids could be playing this game and thinking, oh man, maybe I want to be an astrophysicist. We were promoting it at AwesomeCon a couple of weeks ago and seeing these like 9, 10, 11-year-olds coming up and being like, oh, I want to play this. It actually is influencing kids to learn more about space. So it's been really surreal and absolutely very rewarding.
Well, I can't wait to dive into this with some of my coworkers. And thank you to everyone at Goddard and the Hubble team, and you especially, for creating this beautiful game. Because as I was going through the book, I was just like so excited, and I'm really glad this exists.
Yeah, I mean, it definitely did take a village. I had a fantastic team around me, and we all were there because we genuinely loved it. The team was amazing, and it did take a village to get this out.
Always, with every project, especially space projects. Well, thanks for joining us, Christina. And for anyone out there who wants to get their hands on this game, I'm going to leave a link to the website for this where you can download the PDF and all the other fun accessories, the map and everything. That'll be at planetary.org/radio. Thanks so much, Christina.
Thank you.
Now, we turn from the realm of fantasy, exoplanets, and extraterrestrials to the ongoing scientific search for life in the universe. So far, there's only one planet that we know of in the universe that has life, the Earth. We have the right temperature conditions for liquid water and the right chemicals to allow creatures like us to exist. That's not to say that worlds that aren't like Earth can't have life. It's just that we've never found them yet. And since we know that our planet is a winning recipe, it makes sense for us to look for other worlds that have similar conditions if we hope to determine whether or not we're alone in the universe. Unfortunately, searching for Earth-like worlds with water on their surfaces is pretty difficult, but that won't stop people from coming up with new and clever ways to enhance the hunt. Scientists have developed a new method for detecting habitable and potentially inhabited planets by comparing atmospheric carbon dioxide levels across multiple planets within a system. In human biology, the process of converting oxygen and nutrients into energy produces carbon dioxide as a byproduct, which is why we exhale carbon dioxide. But that's not why we're looking for it in this case. Researchers from the University of Birmingham, MIT, and other institutions found that reduced CO2 in an atmosphere could suggest the presence of liquid water, possibly indicating a planet's habitability. Their research paper is called Atmospheric Carbon Depletion as a Tracer of Water, Oceans, and Biomass on Temperate Terrestrial Exoplanets. It was published in Nature Astronomy on December 28th, 2023. Our next guest is the lead author on this paper, Dr. Amaury Triaud. He worked alongside Julian DeWitt and many others in an international collaboration on this research. Amaury is a professor of exoplanetology and the head of the Sun, Stars, and Exoplanet Research Group at the University of Birmingham in the United Kingdom. He focuses his studies on exoplanets that are unlike the ones that we see in our solar system, things like hot gas giants and circumbinary planets. But he also searches for planets with masses and temperatures that are similar to our planet Earth. Hi, Amaury.
Hi, Sarah.
Thanks for joining me. I feel like humanity has made such amazing strides in the fields of exoplanetology, trying to detect exoplanets, trying to understand them better. But to this day, we still haven't found a habitable world like Earth with liquid water on the surface. Why is it so challenging for us to find these types of worlds?
Well, I would say useful or interesting tasks are challenging to begin with, otherwise we would already have done it. So I think to begin with, this is a question that has been in people's minds, at least in writing, for 2.5 millennia. So it's been a long time in the works. In terms of planets, the issue is more that finding a planet like Earth around a star like the Sun is really difficult. The signal that an Earth-like planet does is absolutely minute. And distinguishing it from the sort of noise, the buoyancy, and the stellar variability that happens from its host star is very difficult. And then beyond that, studying the content of its atmosphere is even harder. And here, maybe I need to explain that. So it's difficult to directly image a planet. So the only thing that we can do is find how the planet influences its own star's light. So it's a very indirect measurement. And in order to find out whether there is liquid water at the surface of another planet, then first you need to distinguish the planet from the star. Then you distinguish the atmosphere from the planet and the star, and then tease out of that atmosphere what is the information that might relate to the presence of liquid water on the surface of that planet. So it's a very complex problem. We have now identified Earth-like, meaning the same size as the Earth, same mass as the Earth, so planets like that, in the habitable zone around their stars. And now the step that is happening is to, one, find out whether they have an atmosphere, and second, then what are the conditions at the surface of this planet. So it's just about coming, and hopefully in the next few years we might have some satisfying answer.
And thankfully, your team has come up with a really innovative way of helping us try to figure out there's actually liquid water on the surface of these worlds without looking for water directly, which is a very interesting thing given all of these challenges. Trying to find liquid water on the surface of a world is something that we really want to do, particularly because of the search for life, but it's just so uniquely challenging. And it occurs to me that probably most of the worlds that we think of as habitable are going to be these ones that are rocky terrestrial worlds. But there is an opportunity for us to find life on worlds that have subsurface liquid water oceans. But we're not talking about that in this case. We're specifically looking for terrestrial worlds with liquid water on the surface.
Yeah, completely. And it's not because I don't like or nobody in astronomy likes subterranean oceans. It's simply because we can't detect them. We don't know how to. And we know full well in the solar system it's taken a lot of effort to find out that there are oceans under the crust of Europa, Ganymede, and etc. And only now are we finding out that some of that water goes into space in the form of plumes. But it took in situ measurements to figure it out. Like doing it remotely from Earth would have been particularly challenging, even though people are trying. I think going there is still the best way to analyze those plumes and find out about the properties of that ocean. So now if we place the problem much further away on another star, an exoplanet, well, effectively what the atmosphere does is becoming a reservoir of what's going on the surface or in the interior of the planet. If the planet doesn't have an atmosphere, then it's as good as just a circle that passes in front of its star, and we won't have much more information than that about that planet. So the atmosphere is really important, and so that's why in exoplanets, we're really concentrating on planets with atmosphere. If they don't have an atmosphere, maybe we'll know a little bit about the surface, do a bit of mineralogy, but not much more than that. If there's water underneath, it's going to be particularly challenging to detect. So yes, let's stick to planets with atmosphere. Now, what's sort of interesting is that you started off with a question about the habitable zone. And I think most people are aware of that concept, that there is an area around a star where the temperature is not too hot and not too cold, it's just right, like also called the Goldilocks zone, where you could expect water to become liquid under Earth-like conditions. That means Earth-like atmospheric and geologic conditions. Obviously, those can change. But that concept of habitability has been studied a lot, but remains really theoretical. And what we did in that paper is try to show how we can bring a bit of empiricism. How can we actually measure habitability? And by what astronomers mean by habitability is the actual presence of liquid water on the surface, not the possibility of liquid water on the surface. So obviously liquid water is liquid water, and people, if we were to fly over it, would probably see it almost in an instant and recognize it. So how would we recognize it without saying it? That's where the difficulty laid. So another concept that somehow society or the public and astronomers are really well aware of is biosignature, the fact that biology will produce some gases as waste on Earth. That biosignature, the most prevalent one is oxygen, O2, and that can be detected from afar. And there's plenty of literature on how to detect biosignatures on exoplanets. And some involve oxygen, some others involve other gases. It's very well and good. And it's weird that for somehow something as complex and even more difficult, I guess, to detect as life, there's something to detect, a biosignature. But to assess whether a planet is actually habitable, that it has liquid water, there were no observation proposed to do it. So there were a couple of ones, but they were really impractical for exoplanets, really, really impractical. One of them was to try to detect the glint of water, a bit like you can see the glint of the sun on the methane lakes of Titan. A beautiful observation, by the way, a beautiful picture for people to look at. But on an exoplanet, this is just simply too difficult to actually be a practical way of assessing the presence of a liquid body. So then we had to think of something else. And the idea we present in a paper you referred to is actually not novel in geophysics. It's something that is very well known for Earth, but somehow had been missed in the exoplanet literature. So what we've done with my colleagues is bring that idea to the astronomical community and say, hey, we can do this. You know, if we look at what we understand about geophysics, actually we can apply that on exoplanets and maybe find out liquid water.
Your team has devised this new habitability signature. Specifically, you're looking for CO2 in the atmospheres of these worlds. Why would the amount of CO2 in an atmosphere give us an indication of whether or not there's liquid water on the surface?
Right, yeah. So the first part of your question was actually interesting. At first, we needed a word. It's weird, but when you don't have a word, we usually don't know what we're talking about. So in fact, yes, we define this based on biosignature as habitability signature. Then it means that we propose one, this CO2, but it means that other people might propose another. That might even be better than the one we proposed. But at least now we're talking about measurable, observable signatures, not the concept, theoretical concept of a habitability. So what we saw on Earth, at least, is, and what we know on Earth, is that there is a lot of CO2 dissolved in the ocean. There is 2 bars of carbon dioxide dissolved into the Earth's ocean. So if you were to remove all that carbon dioxide from the Earth's ocean, suddenly the atmospheric pressure would increase by more than a factor 2. That's kind of crazy, right? More than twice the volume of the atmosphere dissolved in the ocean. And within the crust of the Earth, there is as much carbon dioxide as there is in the atmosphere of Venus, which has an atmosphere of 80 bars, so 80 times more important than that of the Earth. And the reason there is so much CO2 in our ocean and in our crust is mainly because of water. So the carbon dioxide, through the carbon silicate cycle, dissolves into the ocean, then precipitates as the form of carbonates, and then it gets progressively buried into the crust with plate tectonics on Earth. And so that is really rather unique. And we can't think, and through that paper we've been looking at other possible scenarios for stripping our atmosphere of CO2, and we can't find any natural mechanisms that would manage to do that in such quantity. And in fact, it makes sense, right? Because with the current climate crisis on our hands, we wish we had a method to get rid of CO2 from the atmosphere. And we find that this is excruciatingly hard. And actually, the most interesting and constraining pieces of information and evidence we've gathered in that paper actually come from industry, from people who are trying to remove carbon dioxide from Earth's atmosphere and can't do it except if they use water. And so it's very difficult to do any other way. So water is really important. So oddly enough, biology does it too. And so the paper has another component on the biosignature related with carbon dioxide, because about, at the moment, 80% of the carbon that is sequestered into the Earth at the moment is by the ocean, and 20% in the form of biomass by forests and meadows and etc.
That means, too, that byproducts of life like oxygen or ozone could be added as a measurement here to give us an even better indication of whether or not there's actually potentially life or something that could be sequestering more of this carbon dioxide.
Yes, indeed. So like the paper goes on first to explain that idea of habitability signature, and then it goes on to how we can use the James Webb Space Telescope to detect it and plan. And one of the things that we point out is that if we observe in the mid-infrared at 4.5 micron specifically, then you can find CO2 very easily, which can give you first a test that the planet has an atmosphere, what we want to know. 2, then it tells you that you can observe more. Then you find out whether there is CO2 and whether there is a lot or not too much. But then right next to the CO2 feature, there is an ozone band absorption, as an absorption band there. And ozone, like CO2, creates massive signatures in the presence of minimal amount of molecules in the atmosphere. And if that ozone is there, then it would point out to an atmosphere that has a lot of oxygen as well, and thus tell us that some of that CO2 or missing CO2 in the atmosphere would probably have been sequestered by biology as well. So it can be turned, in a way, into a biosignature. So although we started on the idea, let's create a habitability signature, actually some of it can be also used as a biosignature, which is really useful. And the James Webb Space Telescope was launched with one of its primary objectives, trying to assess presence of life in the universe. But many people have become a little disappointed, but first in a number of planets that are at the disposal of the James Webb Space Telescope, but also how hard it is to tease those biosignature signals out of the noise of the planet and the star itself, mainly the star. So by looking at that habitability signature, oddly, we stumbled on this other biosignature, which, interestingly enough, is actually just a little better to observe with the James Webb Space Telescope than many of the other things that people have proposed. And so we're quite optimistic that hopefully our plan of observing some of the planets that we're interested in will be followed, because this is quite convenient. Nature did us a favor, really.
Absolutely. And it's really lucky that the James Webb Space Telescope can actually observe this kind of thing, because similarly to a lot of people, I really wanted to know more about these exoplanetary atmospheres, potentially have a hint at life in the universe, only to find out that a lot of people were saying that this telescope wouldn't be able to give us that information. So finding new ways to actually get that data and potentially suss this out means that we can get even more out of this telescope. Not like we need to already. It's blowing the lids off of so many different parts of science.
Exactly. It's an incredible telescope. But yeah, if we can use it to make that discovery, that would be absolutely fabulous. Yes. Now there's a little more hope that we can. We need to convince our colleagues to, in fact, do it.
We'll be right back after this short break.
Hi, y'all. LeVar Burton here. Through my roles on Star Trek and Reading Rainbow, I have seen generations of curious minds inspired by the strange new worlds explored in books and on television. I know how important it is to encourage that curiosity in a young explorer's life. That's why I'm excited to share with you a new program from my friends at the Planetary Society. It's called the Planetary Academy, and anyone can join. Designed for ages 5 through 9 by Bill Nye and the curriculum experts at the Planetary Society, the Planetary Academy is a special membership subscription for kids and families who love space. Members get quarterly mailed packages that take them on learning adventures through the many worlds of our solar system and beyond. Each package includes images and factoids, hands-on activities, experiments and games, and special surprises. A lifelong passion for space, science, and discovery starts when we're young. Give the gift of the cosmos to the explorer in your life.
There are other things that could potentially impact the CO2 in the atmosphere. As an example, CO2 could be photodissociated by light from space. Is that something that we have to take into account here, or is that such a small factor in the calculation that it wouldn't be important here?
Yeah, it's something that we point out at some point in a paper. So we explore a number of false positive and false negative scenarios. So now I think the public is also quite aware, thanks to the COVID pandemic, of what a false positive is. So a signal that would mimic one that we expect. So here we expect a deficit in carbon dioxide. So we could have a deficit created by other means, which would not be by liquid water. We find that none of those are actually really credible. And false negative, which would be the planet is not stripped of CO2, but does have liquid water, which is harder to assess. So indeed, you could have some photodissociation involved, but what we find is, so first, in a paper where there's an element that we haven't discussed yet, is that what's important to us is that we have to measure this carbon dioxide abundance in a planet of several planets in a single system and then compare them to one another. So if we look, for instance, in a solar system, Venus, lots of CO2, Earth, not much CO2, Mars, lots of CO2 in volume. Earth stands out, and in many ways, we want to be able to do that on other worlds because we don't exactly know what content of carbon they started with. And so doing that measurement in isolation, in absolute, would be very difficult. But then photodissociation, interestingly, scales with distance. So if the CO2 were to be removed by photodissociation, you would expect it would happen less on the outer planet than on the inner planet, and so tease out that signal, or at least correct for it. Photodissociation is important, but not usually the most important, of the processes in an atmosphere. Only a fraction of the molecules in the atmosphere are going to be photodissociated usually. Otherwise, it means that something very bad is happening to your atmosphere and you're probably not habitable, like the sort of world that we're looking at.
The one unfortunate thing about that is that it means that in order to determine whether or not one of these worlds has liquid water, we have to target a system that has multiple worlds in it. Do they have to be terrestrial worlds, or can we use other gas giants and ice giants to help us get an idea of the carbon dioxide content within that system?
So that's interesting. We haven't really looked that far into it. So I think the premise was that we were looking at rocky worlds primarily, but it's true. Other planets would have a sort of balance of the various elements that would probably be useful as a calibration to some extent. But yeah, I won't be able to speculate more on that. Let's leave it as something to check. Hopefully that paper will actually mean, and we talked about it already, because it's now named and hopefully highlighted that we can observe or infer the presence of liquid water on a planet. Maybe other people will come up with other schemes or actually refinements of the idea that we present. It really is an introduction of a new concept for astronomers. Again, that was well known for geophysicists.
Within our solar system, we have very few examples of worlds with thick atmospheres that we can really look at. We have Venus, we have Earth, Titan, but we have very few examples to compare this content between. And what I'm intrigued by is this idea that clearly the Earth has an okay amount of CO2 for us to exist currently. Venus does not. How do we figure out where that tipping point is between habitable and not habitable?
As an observer, again, that's a territory that is hard for me to go into it. This is more of a theoretical concept. Many gases are relevant for the greenhouse effect. So water, for instance, water vapor is by far, I think, the gas that keeps the most heat on our planet. It's just CO2 is the easiest to change. And that one makes a big change really fast, or CFCs as well. So I think one can imagine, normally when you observe a planet's atmosphere, you measure the volumetric mixing ratio of these molecules. So you know how much of the atmosphere is made, say, for us, of nitrogen, how much is water vapor, how much is oxygen and CO2 and all that. And from that, you would put them usually in a model, and that model would tell you what is the temperature at the surface, and that will tell you sort of the conditions for habitability. the approach that we're doing is really because the lack of CO2. Like for us, like the way we see it is that Earth started with as much CO2 in its atmosphere, presumably, as Venus did. And already within the first 500 million years, had lost most of it into water, dissolved into rocks and the crust. So the presence of water, I would say often people have been, and there have been papers before, that were trying to say, oh, how much CO2 should you have on a planet's atmosphere in order to remain habitable as a function of orbital distance? Where we turn sort of that problem around by saying, well, if you find that there is a planet with not much CO2, where has the carbon gone? And the only way that it can have gone is somehow in the water or into the crust via means of water. So somehow there must have been liquid water involved, regardless of whether you think it's habitable now or not, if you see my meaning. So it's a trace of that liquid water. Then the concept of habitability, then I think that's more theoretical. Then you put all your gases together, you find out what the temperature is at the surface. But if water is liquid in that it is keeping the atmosphere low in carbon dioxide, then somehow it must be habitable. Or at least that's how I see it at the moment. Maybe I'm missing a step in my logic, but yeah, time will tell.
Well, I mean, if all of the other terrestrial worlds nearby have a certain amount of carbon dioxide and this one does not, whether or not it's an actual indication of water, something is weird going on there, and I would love to know more, right?
Exactly. That's exactly like when we started off, we are really observers, we're astronomers. And what we want to find is something weird that tells us you need to observe more effectively. And that's exactly what we're saying there. And actually, among the false negatives, we say maybe there is another solvent in the universe that can dissolve liquid CO2 better or as well as liquid water does. But then if it does exist, then that's great, because in our fight against rising amount of carbon dioxide on Earth, we'd love to know what that solvent could be. And so it would force us to anyway question why is there so little CO2 on that particular planet.
And this is part of why we advocate so hard for new missions to places like Venus, because it's not just about understanding our neighboring worlds. This kind of science can have a big impact on the way that we interface with our own planet.
I agree.
So if we combine all these things together, you now have a pretty effective 3-step plan. What are those 3 steps now?
So those 3 steps are to turn the James Webb Space Telescope to multiplanetary systems with rocky worlds, including several of them in the habitable zone. Actually, personally, my take is that I don't really like the term habitable zone, because most people think of it as, oh, I can go and pitch my tent over there and have a picnic. You know, it's not quite like that. I prefer temperate because I think even worlds that are not, habitable, that don't have water, in that sense, would be interesting. Like in the case that we were talking in case of Venus, I think the edge cases, Mars and Venus, same for exoplanets, are really insightful to learn about habitability. So first you need to identify a system with multiple planets, and we think we have one. There's a TRAPPIST-1 system already with 7 worlds. We're working hard to find others similar to that. And then you need to use the James Webb Space Telescope to do at least 10 transits on a few of the planets, preferably starting with TRAPPIST-1E or 1F, which are in the middle of the system and seem to be the best candidates in terms of expected surface conditions. And then you need to observe the planets next to it. So first I would say, let's observe E or F, maybe both, measure the carbon dioxide band and find out whether there is carbon dioxide. If there is carbon dioxide, then it must mean that there is an atmosphere. Then game's on. Then we can start by taking something like 40 new transits or so on that planet, but also on another planet in a system in order to at least have that calibration. And then that tells us already how much carbon dioxide there is in that planet's atmosphere. And we're not looking at subtle effects. We're looking at Venus, 95% carbon dioxide in the atmosphere. Earth, 400 parts per million. Even if we find a planet with less than 20%, already the deficit needs to be somewhat explained. So it's not a subtle effect, and unfortunately for us on Earth, but fortunately for exoplanets, carbon dioxide makes very easy detectable structures or absorption bands. And once we have that, then we can ramp up again the pressure, put more transits, like of order 100, to then really measure precisely how much CO2 there is, but also try to see that ozone band on the side and see whether we have a carbon depletion that is created only by geology or also by biology.
That makes the TRAPPIST system an even better target when we consider the fact that you're going to need a certain number of transits. All the worlds in that system are pretty close in toward their stars, so we'll be able to get those transits a lot faster. But I imagine that trying to get the telescope time for this kind of observation would be rather challenging.
Yes, it is. So yeah, like you point out the right thing. Like we've been with the TRAPPIST Speculoos team, we've been involved with those low mass stars from the beginning because of that, because you can go 50 times faster in a way, because your planets are so much closer to the star. And it fits within James Webb's expected lifetime. But indeed, because you need to acquire so many transits as the planet passes in front of the star, that's the only time where you can measure the atmosphere. And so you're limited. You can't do all those measurements because it happens at most once a week, once every 10 days. You can't do those within a year. So you have to apply across what we call multiple cycles of the telescope. And at the moment, the telescope doesn't have a way to do it. You have every year to ask what you want for the following year, which makes it difficult because when you want to ask for that time, if we were to go straight for the 100, the only thing that you could promise is that you would not find anything this year, that they need to trust you, that next year you will apply again and not find anything either, and then eventually you will find something. So that makes it really difficult. And that's why we came up with that plan of doing it progressively. First 10 transits, then assess, then a bit more, then assess, and then a bit more, then assess. It's easier to convince people. The problem and the downside of that is that it is slow. And we need to remember that the James Webb Space Telescope will not live forever. It has a limited amount of fuel. It gets bombarded by micrometeorites and such. And if we really want an answer to one of humanity's oldest philosophical questions, we have a chance right now. And I think we better take it, otherwise we'll regret it. I think there'd be nothing worse than, fast forward 50 years that we realize we could have done it nowadays.
What do you think are going to be the biggest challenges to doing this kind of science in the coming decades, apart from just getting the telescope time?
Yeah, understanding the star is probably the main challenge besides telescope time. The stars are noisy, stars are misunderstood, especially stars like the star at the center of the TRAPPIST-1 system, because those are stars that are very different from the sun, and they have signals that can mimic atmospheric features. They have things that are difficult to assess. So there is a big initiative run by a colleague of mine who actually co-signed the paper, Julien De Witt, from MIT, to actually gather the community around and accept that we need to understand the star, we need to understand the planet, and come up with an efficient plan to observe this system so that we don't cost too much telescope hours, to allow other astronomical communities to do their science as well and make the most out of what little or what time we have on that facility.
And unfortunately, these red dwarf stars sometimes can be very feisty. They send out a lot of flares in their early years that in and of itself could be a danger to a lot of the creatures that could live in those systems.
Yes, I remain quite agnostic on to these kind of things personally, because the main problem is whether you retain your atmosphere. I think flares and stellar wind, the main issue is whether your planets are atmosphereless, and that's why I think the first element is one, detect whether the planet has an atmosphere. If it does, then I would say anything is fine. Like stuff underwater doesn't care, hasn't seen a photon in their life. At the bottom of the ocean, it's 2 degrees across the Earth. From pole to equator, it's 2 degrees at the bottom of the ocean, 3 kilometers deep, everywhere. So they've never seen a photon in their life. They don't know what star is. So I would say I don't care much about flares and whatnot, so long as the atmosphere has at least remained or got reconstructed later on. I think what is worth pointing out, though, is the stars are weird, and it might seem strange to start by the weirdest star or stars that we don't understand too well, but at the moment it's just we don't have an Earth around a sun-like star, and they're even harder to find. And it turns out that those small stars are 3 times as frequent as sun-like stars. And it turns out also, and those numbers are really rough and prone probably to revision, but at the moment it seems that they have 3 times as many rocky planets. So if you count all the rocky worlds in a galaxy, out of 10, 9 will be around these red dwarfs and 1 around the sun. So if we want to find out how often is there biology in the cosmos, not just is there biology, but how often is there, then if we find out that none of the planets around red dwarfs have, atmospheres, then we'll know that at least, at most, 1 planet in 10 could have detectable life. So that limits, that's already a huge number. As the first order of magnitude, 1 in 10. To do 1 in 100 will take a really, really long time. So it's essential to start with those. And that's why, what I find is that a lot of people are obsessed with detection. They want to detect life. But I think a non-detection in this case is just as invaluable information, because in our quest to understand how life started on Earth and why are we around a sun-like star, we need to understand those little red dwarfs as well. Could they be either the biggest host of biological oases in the universe, or are they all barren? And it means that sun-like stars are the real targets, and that's why we're around one. That's the sort of answer that eventually we can tease out of that, even with non-detections.
But wouldn't that be beautiful if there was a higher chance of having terrestrial worlds around these types of stars? They have much longer lifespans than larger stars, so that could potentially be a safe haven for life for billions of years to come.
Yes, it could be. Yes, indeed.
But all very theoretical. We're just at the beginning of this beautiful journey toward figuring these things out, and I'm glad to have a new tool, because we all want to find life out there in the universe. We want to find our own world reflected out there, and the fact that we haven't found one yet just makes me want to search even harder.
Doesn't it? Yes, same. I want to find out before I die, certainly. That's why I go for red dwarfs faster. And then if we don't, then okay, we haven't waited to find a planet around the sun-like star, which will take a while. It's so difficult.
It is, but we're taking next steps. What is your group's next steps in this? Are you actually trying to get telescope time to figure this out? Or you've already said that you're working with some of the other teams that are trying to get this data on TRAPPIST-1.
I'm involved in the Speculoos survey. So Speculoos is a series of telescopes around the world. A prototype was TRAPPIST, which found TRAPPIST-1. So it's a long-haul project, and that it will take 15, 20 years to survey all the red dwarfs that we have north and south. But we expect to find out of that sample something like 20 to 30 other rocky worlds. So when you account for TRAPPIST-1 in that sample, which is in the sample that we envisage from the start, then we already are counting 9 rocky worlds detected with a telescope around such stars. So we're doing well. We're already half or a third of the way. We have more stars to cover. Some of them would be great for James Webb. So yeah, we'll see. We were just discussing actually just earlier on detection methods, etc. So I think people should be on their seats waiting for our next discovery. So that's the main thing.
If this method in any way helps us find a world with water on it, that would be one of the most amazing breakthroughs in our history exploring the universe. So I'm really happy to have you here with us to share this. And hopefully you've inspired other people to want to help in this effort and use this method themselves.
Yes, thank you very much actually for your interest in it, and indeed for amplifying our message in a way. Here's a new area. Please get involved, do research, tell us whether this idea is one, good or bad, implementable or not, and find other habitability signatures, because I think empirical traces of liquid water would be dearly needed to direct our efforts, our telescope efforts.
It'll be a multi-year, multi-decade effort, and we're going to need more than just one detection on one place to actually prove that life is out there or that there's water on a world. But the fact that we're even this close at all, when just 20 years ago we'd barely started finding exoplanets, is just absolutely remarkable.
Indeed.
Well, thanks for sharing with us, Amaury.
Thank you, Sarah.
Now, let's see what our chief scientist, Dr. Bruce Betts, is up to and what's up. Any guesses as to whether or not he's a fan of tabletop roleplay games? Hey, Bruce.
Hello, Sarah. How you feeling?
Ooh, I'm getting there. I caught a little bit of a something while I was hugging people at Eclipsorama, but totally worth it.
Ew, gross. That's why I covered myself in saran wrap while we were there.
Yeah, life on Earth is pretty gross, but still amazing.
There you go. No, it's amazing. There's no doubt about that.
Yeah. So in the show, I got to talk with Amaury Triaud about this cool new idea about ways to find water worlds, or specifically terrestrial worlds that have liquid water on their surfaces. It's interesting because I feel like there's so much potential for looking for life out there in the universe, but we're kind of in this Earth-centric kind of mentality about it because it's the only planet where we've found life so far. I don't know. Do you think like we're more likely to find life that's Earth-like? It's hard to even guess.
Yeah, no, all of those questions are so hypothetical. To me, what I understand of it, it seems likely in that Earth life found a really good set of stuff to use to power itself and form molecules and uses liquid water as a solvent, which is really good at it to do your chemical interactions. And so it seems not unlikely to me, but then we don't know. That's what's exciting.
I remember hearing in a planetary science class that, part of what makes water so useful for this is its chemical properties, the way that it interacts with other chemicals. But what's really cool about it on Earth is that it exists in this kind of triple point where we can have both gaseous water and frozen water and liquid water. And that you would need some kind of, if you were going to be looking for life on another world that wasn't water-based, you'd have to have some kind of scenario like that for it to work. And it gets more and more complicated as you climb up the periodic table.
Yeah, water, I don't have a specific comment on that, but water's just got some amazing properties, and we often take it for granted, but some of them are relevant and some aren't. But it's got does chemical actions really well, which is relevant, but it also takes a very large amount of energy to change its temperature. Here's a neat thing. It forms ice on top. Ice, the solid form, is less dense than the liquid. And that's kind of cool because then you're less likely to freeze your oceans or your lakes. And one thing, all life on Earth, if it is Earth life, as far as we've found so far, requires liquid water. Not just water, but liquid water at some point in their lifespan anyway.
That was a cool topic, but my nerdy heart was really excited to talk to Christina Mitchell about the Lost Universe. Have you heard about NASA's new tabletop RPG?
No, I have not. That's a wild concept, I think. So tell me stories.
Well, it's the first time they've ever done anything like this, which is funny because I don't know how many times this has happened to you. I should probably ask you first so everyone knows this. Are you a fan of tabletop roleplay games?
No, not at all. I find you to be a freak. No. Yes, I am a fan, and most of that has been Dungeons and Dragons, but I have various editions. But I have done others. I do find them entertaining, especially if you end up with the right set of people. It can be a big fun.
So many times I've tried to play these games with my friends, and we want to do a space version of it, so we'll end up creating some kind of weird homebrew set of rules. But essentially, the Hubble team at NASA Goddard decided that they were going to try to create a roleplay game that you can play on top of one of these other tabletop roleplay games. So say you're using the rules for Dungeons and Dragons, but you're playing in this world where suddenly the Hubble Space Telescope is disappeared, or you're on a rogue planet careening through the void. And I'm really hoping that we get a chance to play this together sometime.
Yeah, that sounds wild. I'm reminded one of our regular listeners has developed some, not only D&D, but a thing called The Strange. I don't know if you encountered it, but you have such flexibility to add things on top, whether it be Sherlock Holmes worlds or Rogue Planet worlds. Anyway, that's just a side note.
So cool. One of these days, you, me, the rest of the planetary crew will be playing that game at HQ. I can see it already.
I can see it, and I can see you just destroying us all with your rogue planet.
You know me too well. All right. What's our random space fact this week?
It's a random space fact. So during that eclipse thing, a lot of people who didn't have total clouds and had proper looking at the sun stuff, when you hit total eclipse, there were those orange things off the edge in some places. Those were prominences, which are these basically material that comes off the photosphere, kind of the closest thing to what we call the surface of the sun, and extend thousands, at least, kilometers, and as many as the longest measured is hard to even imagine, was about almost a million kilometers long. and they're plasma charged material like the rest of the sun, but following magnetic fields out there, and they form in like a day type time frame or days, but they can actually dissipate over months, which I find amazing. And they're cooler than other stuff, so you don't see them normally until you stick the moon in front, and just like you see the wispy corona, you can see a few of these prominences if they're sticking their heads up.
That was a crazy experience. All of us just waiting for the clouds to part. And then I was standing next to one of our colleagues who looked up and it was like, what is that thing? I'm like, that's a prominence. And just being able to see it with your eyes, it's next level. That was so cool.
Yeah. So I'm guessing you enjoyed the eclipse, Sarah?
Nope. Hated it. No, it was amazing.
Oh, all right. That's what I figured. Space
Did
stuff
you
just does not inspire you. Yes, I enjoyed it very much. It was quite the dramatic effect of clouds. Won't they cover the sun? Will they appear? People cheering, lots of great, enthusiastic Planetary Society members. It was a great experience. And I assume you had one, too. In fact, I know you did, despite what you say.
Well, I'm sure we'll get more into it next week when we take everyone on this adventure to Eclipse-orama, but I'm very happy I got to experience that with you, Bruce.
And I with you, Sarah. That was fun with you and all the Planetary Society staff and lots of members. It was big fun.
It was. All right, let's take this out.
All right, everybody, go out there, look up the night sky, and think about noodles and what you most like to do with them. Thank you, and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with a trip to our Eclipse-orama Festival in Texas. We had such a great time. Thank you to all of the Planetary Radio fans that I met along the way. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review and a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email at planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members who look to the stars and dream of distant worlds. You can join us as we continue to scientifically search for life beyond Earth at planetary.org/join. Mark Hilverda and Ray Paoletta are our associate producers. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. And until next week, Ad Astra.